Oh, really? All right. Welcome back from the lunch break. And we continue with a double feature. So we have Alex and then Andras tell us all about the distillation teleportation protocol for fault-tolerant QRAM. Please take it away.
Yeah, so I'm going to talk first about the overall protocol, and then Andras is going to take over and talk about the distillation part of the protocol. And this is based on a paper that's on arXiv today, and it's joint work with a bunch of other people. Most of us are affiliated with the AWS Center for Quantum Computing. And yeah, so let's get going. So the topic is QRAM. And so I'd like to motivate a little bit why we should care about QRAM and what is QRAM. But first, I want to talk about RAM, classical RAM. And of course, in our normal computers, we have a lot of different kinds of memory, varying kind of latencies and sizes and whatnot. But all of them sort of boil down to the same abstract operation, this RAM operation, which does the task of retrieving one of 2 to the n data items when presented as input with the n-bit address indicating which location in memory. So as an example, right, if you pass your RAM chip the bit string 101, it should find this bit 1 stored in the memory and give that back to you. But importantly, it should happen very, very quickly. And there's this sort of assumption that we use often when we analyze algorithms that the access time or the cost of RAM is, even sort of unit cost, but definitely polynomial in the number of bits of the address rather than the size of the memory. So kind of logarithmic in the size of the memory. And this bears out because we can build actual chips that actually do this in kind of a matter of only a few clock cycles, or tens of, just a few nanoseconds. Oh yeah, that's 1. So QRAM is the same thing, except that we want the input to be a superposition of different addresses. We want to have the same kind of functionality, even in quantum superposition. So we want, given this arbitrary input state, we want to append a -1 phase on the computational basis states that correspond to a row in the data table where the data is 1. Now, this is sort of equivalent to other formulations of QRAM where you might have a bus register that you read the information into. This sort of phase version of QRAM captures really the full difficulty of QRAM, and you can reduce the other versions to this one. So we're going to focus on this one for simplicity. And you'll notice that it's a unitary operation, which we denote V of F. It's a different unitary for each possible data table that you could write down. That's why it depends on F. But it is unitary, and it's actually a diagonal unitary with plus and minus ones on the diagonal. Right? As an example, if we give a superposition of 4 entries of the data table, we should retrieve as output the same superposition with the minus ones in 3 of the 4 basis states. And there's this sort of controversial assumption in a lot of algorithms that depend on QRAM, which is that the cost of doing this operation is similar to the cost that we assign to RAM in classical computing. So it has poly-n computational cost. And there's sort of a lot of quantum algorithms that if this assumption were to fail would not be able to deliver the speed up that they're promising. So it's sort of an important question to get to the bottom of. Okay, so when we think about evaluating this assertion that QRAM has only polynomial cost in the number of address bits, we can try to motivate it by writing down a quantum circuit that implements this unitary in only order n depth. So this is one example of such a circuit. This is actually only half the circuit. You have to kind of do you have to do the inverse of this circuit after that one, but it only has order n depth. And so if you could perform gates in parallel and perfectly, then you would be able to implement this in only order n time, and you could achieve the kind of latency that we see in classical RAM. You'll also notice some features of this circuit that it consists of almost entirely of controlled swap gates, which are non-Clifford gates, but not really alone capable of universal computation. And it also has a certain property, which I won't get into, like a noise resilience property, which is actually quite important for the story of QRAM. Yeah, you have to go into that paper to look into that. But it has some big drawbacks as well. First and foremost, in order to achieve this really shallow depth, it requires a very large overhead of space. So you need order 2 to the n ancillary-qubits. You need order 2 to the n total gates. A large number of gates have to be non-Clifford. If you were to imagine doing this on an actual device, you'd have to account for the fact that there would be errors. So you might try to do this circuit fault-tolerantly. This would require you to encode each of the 2 to the n ancillary-qubits into its own set of physical qubits, leading to a device size that is enormous. So previous estimates, for example, have suggested that quadrillions of physical qubits would be needed to build an 8 gigabyte QRAM. Yeah.
Like, how do you tell it about F?
Oh, yes, good question. So F only comes in this row here. Basically, if the value at address 7 is a 1, then you apply the X gate, and if it's a 0, you don't apply the X gate. So this would be an identity or an X, depending on the value of the data. Yeah. But the routing part here is independent of F.
So I should just think of these as all C-naughts to the register that store in the X's.
Yeah, you could think of them as C-naughts, but it's like classically controlled. So it's not quite a C-naught. Like you have kind of we're only talking data. Yeah, exactly. Yeah, yeah.
So if I need like 2 to the n gates, what is the argument that doesn't just completely destroy the claim of a quantum speedup?
I guess the argument is that classical RAM also requires 2 to the n gates, right? And we see in practice that it works, right?
But it's not really gates that it's well. I mean okay. So maybe what we could say is that yes, in some sense there's 2 to the n gates, but only one of them is active at a given.
Yeah, and this circuit has a similar like property as that one, right? This like activeness that if you
good.
So there is a sense in which if you were to do it fault tolerantly, you would kind of lose this, because you don't know which path it's taking in the quantum case, so you have to kind of be prepared that it would take any path.
Right. Well, it could be taking a superposition.
Yeah, exactly. Yeah. And then I think an underappreciated point of this as well is that if you were to do this fault tolerantly, you would need to also spend a lot of classical resources doing error correction on these immense number of ancillary qubits. And there's like an opportunity cost of this. You could just apply that classical parallel processing power directly onto whatever computational problem you were trying to solve with your quantum computer. And this point is made very clearly in this critique of QRAM from 2023. Yeah.
Isn't the 2 to the n asymptotic also somewhat like scarier than it actually is, because you would also have needed to do the classical computation to produce those 2 to the n entries, right?
Yeah, I guess in many like of these like end-to-end applications, there would be kind of a pre-processing step. But I mean, I guess this doesn't totally often we're looking for like an exponential speed up, right? So we have like this classical data set, which is very large, and classically we would like process it linearly, or there'd be some like, you're doing some like matrix inversion or some linear algebra task where you're kind of storing an entire vector worth of classical data. And then the quantum algorithms work by kind of taking a logarithmic number of qubits, somehow encoding the data into the amplitudes and only doing a logarithmic number of steps along the way. And so, yes, I guess there would be a pre-processing point, but I don't know. Like if you're in a situation where that's a problem, then the exponential speedup is already not available to begin with. I'm not sure that answered the question.
Well, I think. I guess what's the intuition for why we would hope for there to be a logarithmic, right? So if you use big N instead for the the rank of the input, doesn't that mean that, like you were saying, you want something essentially logarithmic in that input, that big N?
Yes.
What's the intuition for why that would be feasible generally, right?
Well, so I think we assume this implicitly when we analyze classical algorithms, right? That like we have a big classical data set, maybe we've created over the course of the algorithm, but then we can just grab any entry we want from the memory that we've created without paying linearly every time, right? Like if you have T accesses to a memory, you only pay T costs. You don't pay T times N costs. So yeah, maybe there's like an order N cost to prepare the memory, but then you don't have to keep paying for that every time you query it. You only pay order 1 every time you query it. So we would like a similar situation for QRAM. Yeah.
Question, sorry, maybe I don't understand the model. Where are the inputs stored? In a classical register, in a quantum?
Yeah, so the memory is classical. So like we're definitely going to have this memory stored in a classical database, and that's like where it lives in this like abstract model that we have. Now, I don't want to get too into the details of like physically how you would make a QRAM device, but like if you look at this circuit, you need to take this classical information and like distribute it to like controllers that are living at each of these physical locations, so that it can decide whether to apply this X gate or not. Like that's like one way, but maybe there's other ways, right?
So some of these wires that are shown in this circuit are classical.
No, all of these are quantum wires. Like what's not shown is that there's like this X3 is like a classically controlled X3, where like if the third entry of the database is a 1, you apply an X gate here, and if it's a 0, you apply identity. So there's a classical control going on. Yeah. Okay. Yeah, let's keep going. Okay, so this circuit approach to QRAM has issues. We would like ideally to have like a specialized approach to QRAM, where we build a device that only does QRAM. We don't do it on a general purpose processor the same way we do every other quantum algorithm. And in fact, there's been like some work on trying to show some of these routing elements in different hardware platforms, of like how you would actually go about building a QRAM. None of them are like fully convincing, but it's in the abstract, it's plausible that you could build a device that performs QRAM in this specialized way. But what's not plausible is that you could build one that has perfect fidelity and that you could like forget about errors completely in your quantum algorithm.
Sorry, maybe this was obvious to everyone else, but like this is literally just the Grover oracle, right? Like it's flipping the signs.
Yeah.
Okay.
It's a phase oracle. Yeah. I guess the conceptual difference is that often with Grover's oracle, it would be instantiated in a way that doesn't require this exponential complexity. Like it's like,
okay, it's a machine that produces one Grover oracle for every input.
Yeah, this is like the ultimate Grover oracle, which can encode any Boolean function, rather than like it's implicitly going to be like a SAT.
Okay, but doesn't that
formula or
already
something.
tell us then that it should be like exponentially large, right? You can encode any Boolean function.
Well, this is okay. We definitely know that it requires an exponential number of gates.
Yeah.
Like there's an exponential number of degrees of freedom. There has to be an exponential number of gates, but the same is true of RAM. I think the important thing here is we wanted to determine if QRAM equals RAM or if there's a fundamental difference. Okay. And we already know that RAM is sort of possible. So we're trying to decide if what's different about quantum that could make RAM QRAM harder.
That physical stick of RAM in my computer actually have like a quadrillion gates in it. Right?
It doesn't have the overhead of error correction, but it does have it has components for every possible memory location, right? If you double your RAM,
right, but
the chip has to get higher.
Components for every set of memory locations, right? Isn't that where the exponential is coming from?
No. So there's n. I think it's important here because there's different conventions, but n is the number of addressed bits, and 2 to the n is the number of memory locations. So, like your stick of RAM would scale with 2 to the n in its physical size, but its latency only scales with n, or even sort of not at all the way they're built.
Right. I mean, I think it's very tricky because classically we could say that RAM is not scalable, right? It's like, eventually latency is going to kill you. It's going to destroy the unit cost model, right? It's just that, there is some intermediate regime where that's a valid assumption, right?
Because of the speed of light, like
exactly.
kind of,
yeah. Right.
Yeah, that's true. So, that's true. But yeah.
Like, are people envisioning like connecting like physical QRAM to like bunch of like surface code or something? Like how do you like have a physical QRAM and like a fault tolerant?
Yeah, okay, that's like I guess the topic of the rest of the slides. Right. People have imagined doing circuits like this one in a fault tolerant way where each wire is itself encoded in a surface code or something like this. And people have also imagined, how do we build a physical QRAM device that maybe has some errors but like achieves fairly high fidelity? Like this is a question that people have studied. But there hasn't really been a way of integrating these together. Like if we actually had such a device, how would we actually use it inside of a fault-tolerant quantum algorithm, which queries the QRAM operation, 1 million times, right? Because we're not going to have fidelity with that many nines. We might have 99% fidelity. We might have 1% fidelity. How do we make use of this? So that's kind of the open question, right? How can we use this device without prying it open and error correcting the individual components of it? Okay, and so our protocol is gonna do that. This is like a schematic, I guess, of like the components that you would need in the protocol. Right, we're going to have the physical QRAM device, which performs QRAM potentially with imperfect fidelity at the physical level. And then separately, we have a general purpose fault-tolerant quantum computer, maybe based on the surface code or something. And the physical device will have to send states to the fault-tolerant general purpose device. It's also an iterative process, and it requires like classical feedback. So it's going to make measurements, and then these measurements will need we're going to have to update this data set and then iterate on an updated data set. And I'll explain that as well. But that's just kind of what it looks like. And yeah, there's going to be 5 steps. Did I mess it up? Anyway, okay, yeah, there's gonna be like 5 steps to the protocol, and they're gonna repeat in this iterative way. So I'm gonna go through each of them next. So, but before I explain exactly how it works in our protocol, I just want to review how it works for the T state, how we do T state distillation and teleportation, because in some sense, the protocol is like a direct generalization of this. Right, the important thing for this is that we define these things called magic states, which are just the equal superposition of 0 and 1 with the T gate applied to the equal superposition, giving us this state shown here. Now, this can be prepared with kind of a multi-step process where you prepare a physical T state, and then you encode that physical T state. There's terms like magic state injection, magic state cultivation, magic state distillation. Distillation is what you do to kind of improve the fidelity of these states. But once you've prepared a high fidelity encoded magic state, you can then apply the T gate onto an arbitrary state alpha by making an entangled measurement between the state alpha and the T state, as shown here. This gives you a measurement outcome M. If M equals 0, you can easily see by direct computation that you've correctly applied the T state, the T gate onto the first wire. But if M equals 1, which happens with 50% probability, then you apply the wrong gate onto the first wire. Instead, you apply this XTX gate, and you have to make a correction for that. So the correction that you have to do is the phase gate, this S gate. So conditioned on getting a measurement outcome of 1, you apply the S gate on the first wire. And the S gate is a Clifford gate, so usually it's easy to perform the S gate in a fault-tolerant way. So the QRAM process is going to be very similar. We define these QRAM resource states, which are generalizations of the magic state, in that they take the equal superposition of all 2 to the n address settings, and they apply the ideal QRAM operation on that. So you get this kind of phase state shown here. And the way we're going to prepare these states is also kind of analogous. We take our physical QRAM device and we run it on the equal superposition state to prepare a physical version of this QRAM resource state. Then we're going to take our general purpose fault-tolerant processor, and we're going to move this n-qubit physical state onto the processor, where we kind of shown a separation here because we're going to encode each of the physical qubits in this n-qubit state individually into its own n-qubit, into its own quantum error correcting code. So here I've shown kind of the surface code for simplicity, but really the protocol is agnostic to what code you use here. The important thing is that there are ways of doing this encoding for the surface code, and in fact for any code, which incurs some error, but in kind of a manageable way. And then finally, what we get out is an encoded approximation of our resource state, and we have to do a distillation process to improve the fidelity of this encoded resource state. And so Andras is going to talk about how we do that in the second part of the talk. Yeah, I guess here we're just going to say, like, assume now that the distillation has managed to output a state with high fidelity with this resource state. And I'll note that like these first 2 steps have errors, right? The physical QRAM device will have errors. The encoding step will also cause logical errors, right? Because it begins with a just physical unprotected qubit. So of course there's going to be errors over the course of encoding. But then everything after that is done fault-tolerantly on the normal way you do fault-tolerant quantum computing. So the distillation is entirely done fault-tolerantly, and it's kind of done to correct the errors that occurred in those first 2 steps. Okay, how do we actually use these resource states? Here, I've just recalled the definition of the resource state and recalled the way we did T-gate teleportation. Because the teleportation of the QRAM states is going to be very similar, we just do an entangled measurement between an arbitrary n-qubit state on which we want to apply QRAM with our QRAM resource state, these n CNOT gates. We make a measurement on each of the n qubits. This is all done fault-tolerantly on encoded states, so we can neglect any errors during this step. So we obtain a measurement outcome m, which is a bit string of length n, and each of the 2 to the n possible measurement outcomes is obtained with equal probability, uniform probability. And we can note by direct computation, similar to the case of the T-gate, that if we get the measurement outcome 0 on all the bits, then we've actually performed the correct gate on the top register, and we can be done, right? We did it. However, most of the time, we're actually going to not get that outcome. We're going to get some other outcome, and we applied kind of the wrong phase onto the first set of qubits. So very similar to the T-gate, when you get a non-zero measurement outcome, you did something slightly incorrect, and you need to do a correction for that. So I guess one of the key things that we've noticed in this protocol is a way of doing the correction in this like a recursive way. So in particular, if you notice, the phase that we applied was -1 to the f of x, or m. So basically, we've shifted the address by some bit string m. So if we could just apply the phase, this phase, -1 to the f of x, or f of x, or m, it would cancel out the phase we applied incorrectly and put back in the phase we wanted to apply. So this correction operation would be the one we want to apply after doing the teleportation of the previous slide. This is the analog of the S gate in that first example. And you notice that this is also a QRAM gate. It's just a QRAM gate for a different data set. So in particular, if we started with this data set, we want to now change the data set to be this one so that we can apply that operation. And you can see here it's a pretty simple update rule where based on the measurement outcome m, we're just going to pair up different entries of the data table and update it in this like simple way. So in some sense it's simple. In other sense it's very complex because we have to touch every entry of the database. So we kind of have to spend like a classical complexity that's scaling linearly in the size of the database rather than in the number of address bits. Yes, question.
Maybe you are getting to this, but you have a superposition over all bit strings x, where in front of it you have this phase, right? -1 to the fx plus m. Why don't you just apply Pauli x to the m to your register? That would shift everything.
Because it wouldn't work because it would also change this alpha x can be yeah. So that would work for the resource states because the resource states have equal superposition. All the alphas are the same. But for this arbitrary state, that would not give us what we need. Yeah. Okay. So yeah, we have to apply this update rule, and we propose to do this classically. So this is not quantum complexity. This is just you kind of have your data set stored in memory and you just update it. Right. So now we can state exactly how the protocol works in a complete way. So we have this diagram here where we have our wire on the top that we want to perform QRAM on. We have our classical wire on the bottom, which stores our 2 to the n bits of memory. We have our several steps here, right? So we have physical preparation with the device, encoding into a quantum error correcting code, and then distilling these resource states into a high fidelity encoded resource state here. We teleport that into the first register. We've applied QRAM up to a correction. So now we do that correction. We take the measurement outcome m, we transform the data set in this way to get this new data set, and then we repeat the process for the new data set. Of course, the problem is the correction may need a correction of its own, right? We have a correction to the correction. So we repeat this process iteratively many times, right? So we might get another measurement outcome, and then we update the data set again. And we keep going. But we claim that you need to iterate at most n times before you can stop iterating because no correction is needed anymore. And here we can actually see this in this particular example of sequence of measurement outcomes that you end up with a data table which is sort of trivial after 3 updates. It's the table with all ones. And this is not a coincidence. This will always happen. It will always be either the all ones or the all zero table after n updates. and then you don't have to make any more corrections. Okay, so maybe I will pause for a second to see if there's any questions. I'm going to try to convince you on the next slide of why it terminates after n.
So this still uses exponentially many number of encoded qubits, but is the point that you don't need to apply all these gates in a fault-tolerant way?
So it doesn't use an exponential number of encoded qubits. There's like implicitly maybe like an exponential number of qubits inside of this box, right? Inside of the like physical QRAM operation. But they're not encoded. They are done at the physical level only. And yeah, they could potentially be like kind of done very naturally without in like very specialized way. So yeah, you can't get away from this exponential complexity in some sense because you know that there's an exponential number of degrees of freedom, but you can contain that entirely to a physical process. And you don't have to spend that much in fault-tolerant resources. Yeah.
So the hope, right, would be that you could do an optimal control scheme to prepare those physical states, right? So that you can tailor it directly from that.
Exactly. Yeah, exactly.
But then would there also be concerns with respect to the locality of the state prepared? Because if it's highly entangled, right, then that may, again, make it non-trivial to prepare that state in the end, right?
Yeah, I mean, it would be highly entangled. You know, if you look at this circuit, like any kind of QRAM implementation would have to have some resemblance to this circuit. It's like a binary tree. It has these non-local gates. The entanglement would be created from these non-local gates. I mean, you know, this is what normal RAM looks like too. Like if you look inside a normal RAM chip, there's like a tree, and it's these long wires and like non-local connectivity. You know, it's kind of inevitable to have that in some capacity.
Yeah. So the savings is really just the lack of requirement for the error correction in there, and then the hope that you could do some physical gates.
Yeah. I mean, it's the lack of you know, before there was like not even a way to use a physical device that had like 90% fidelity at all. So now we can. It's like if experimentalists can come up with a way to build one, it could be used with this in this way. Yeah. Okay. Yeah, I guess just to maybe quickly say why it terminates after n rounds. The reason is if you were to expand this function f, this Boolean function, in terms of its bits, it's a polynomial, and then you were to expand this other Boolean function with the same, but like transformed by this measurement outcome m, you get a different expansion, but the highest degree monomial, the last one, is the same. So then when you add them together, in the update rule, the highest degree monomial cancels out, and the degree is reduced by 1. So maybe for the sake of time, I'll just continue and say, right, so if you believe me that the degree of the function decreases by 1 each time you apply the update rule, and the degree can be at most n at the beginning of the protocol, then you have to apply the update rule at most n times before you end up with a Boolean function of degree 0, which is a constant Boolean function where you don't have to apply the correction anymore. An equivalent way of seeing this is that the QRAM unitary is in the nth level of the Clifford hierarchy, which is maybe surprising because it requires 2 to the n gate complexity, but it actually doesn't climb that many levels of the hierarchy due to its structure. Okay, and now I want to get to this part because it might be relevant for Andras's part of the talk. Andras is going to talk about how we do the distillation, but we do need a particular assumption. We do have to make a particular assumption about what the errors look like in order to apply these distillation methods. And so in particular, we make an assumption about the physical QRAM device, which is that in some sense, the noise is not dependent on the data set. That we're completely general about how the noise looks, but it should have the form of some noise channel, N1, followed by the ideal QRAM channel, followed by some other noise channel, N2. And N1 and N2 can be like they can have a lot of noise, but they can't have noise that depends on the function f you're trying to query. And now there could be ways to like weaken this a little bit so that there's some dependence on f, but here for simplicity, like this is what we assume. And then given that assumption, what we do is we do what we call a partial Clifford twirling of the QRAM gate. We call it partial Clifford because we don't use the entire Clifford group. we only use the part of the Clifford group that's that's generated by ZX, controlled Z and controlled X. Doesn't include the Hadamard or the phase gate. And then the idea is we choose a random Clifford gate. We transform our data set such that this resource state for the transformed data set is related to the resource state we want to prepare by the gate C, which is an n-qubit Clifford gate. And then we query this other data set and fix it up after encoding. And by choosing C randomly, we're kind of averaging over many different configurations of the data set. And this is a sort of a diagram of how this works. It's like kind of an augmentation to that previous figure, where given F, we actually generate a random C, we transform the data set, we query the transformed data set, and then we apply this logical Clifford gate only at the end. So why do we bother doing this? The reason we want to do it is we want to guarantee that this state we prepare at the end of the day has as its principal component the correct resource state. So we don't really know anything about this state because we haven't modeled the device, the noise on the device very well. But what we do know is that the largest eigenvector of this mixed state is the state we wanted to prepare. And also, like we'll say as kind of an assumption that its fidelity is F. And F could be very small, but it should have this property. Right, so I guess just as an example, right, like when we're trying to query the data set on the left, we're actually going to query these other data sets where we choose them randomly, and then we're going to fix them up later. So there's kind of an averaging here over many different configurations of the data. And then this is what Andras is going to talk about. We can then just purify these states and like make the largest component larger with a process that doesn't really even care what that largest component is. So it's like state agnostic. And we pay this 1 over epsilon costs to achieve error epsilon. Okay, let me just conclude, and then we can maybe see if there's any questions after that. Yeah, so the key result, right, is if you imagine you had a quantum algorithm which needed to query the QRAM operation a polynomial number of times, even though the data set has exponential and n size, then you could do that with our protocol, and the cost would be these polynomial number of calls to this specialized noisy QRAM device and a polynomial number of fault-tolerant gates. So there's no explicit exponential cost. Now there's maybe like an exponential cost implicitly inside of the faulty QRAM device, depending on how it's constructed. But we know that RAM at least can be built in such a way that kind of this polynomial cost of the device itself is reasonable. So, now the onus is on the experimentalists for realizing, building this device in that way. We also note that the specialized device can have very low fidelity. It could have even like vanishing fidelity as long as it has at least 1 over poly n fidelity, and the statement would still be true. And yeah, I don't know, it motivates this kind of picture of quantum computing where we would have a specialized component for QRAM, which is kind of unlike other quantum algorithms, where there really aren't that many examples of cases where we're going to do part of a quantum algorithm differently than the other part. Right? We kind of just imagine a sea of qubits and then doing all the gates in the same way, typically at least. But the key drawback is the need for this like classical update, which requires touching all of the entries in the database. So it would appear to have exponential classical complexity. Seems to be harder than RAM. So it would kind of limit maybe the scope of where this could actually provide an advantage.
But that exponential complexity is already there, no? Like in the image that you showed before of a bucket gate with swaps, you have to have a classical control to execute that gate or not.
Yeah.
Really there somehow.
Right. So this is another I guess, objection at the level of like, we're never going to be able to build a physical device that can perform QRAM at only poly n cost, right? We're never going to the cost of this would be poly n calls times the cost of 1 call. And what you're saying is like the cost of 1 call would already be exponential in n because you would need this classical controller. And I think that's true for most of the proposed ways. But you could imagine like a more passive way of building a QRAM, where like you just build a device, you pre-manufacture a device with like static elements, and then you just like throw in some photons or something, and they like are routed through this like static system. And then they come back with the phase, right? Like, I don't think it's a priori impossible to imagine that not needing a controller for every.
I mean that is the idea that I had seen, that you just have like a photon that spreads out in a superposition and comes back with phases attached.
Yeah.
But I mean, you say the key drawback is 2 to the n classical computation, but is there any lower bound saying that that's inherent?
Yeah. So in the paper we do like some like kind of comments on this. I mean, there's definitely not like a lower bound. I would say there's like a fundamental issue with QRAM that RAM does not have is you need to protect the information about which address you're querying, right? Because you need to be able to query a superposition of addresses. You can't copy the address. You need to protect that. And so you can't, the physical device will like inherently expose the address information to an error by fanning it out into like many different physical locations. And our protocol gets around that by like doing this resource state, which is an equal superposition of all the different addresses. So it manages to kind of hide which one it actually wants to query, because the resource state is always the same, independent of the address being queried. But the kind of cost of that is that we have to do this, like there's non-local information about the data set we have to get back in, and the way our protocol handles that is by touching all of the entries of the database and like reconfiguring them. It seems like it's fundamental for like this protocol, but I don't know if it like is actually needed. Yeah, question.
When you do the corrections, you're kind of doing them on a smaller function, right? Because you've taken this function you've sort of taken every pair of indices x and x plus m, you've made them the same. So you're kind of halving the size of the domain. So could you use a smaller QRAM for doing the corrections? Like size of the QRAM as you go along?
Yeah, okay, that's a really good question. In the paper, we didn't like mention this at all. But I think the answer is yes. I think that like you do have like half as many degrees of freedom, and you could query a QRAM of like half the size, and then like apply a few gates to kind of like make it bigger. Yeah, I think you could. Yeah.
And this isn't thought to be for the asymptotic regime, right? Because you would imagine that the fidelity goes down something like 1/2 to the n, right? Like you would expect it to be super exponential and decreasing, like with the earlier discussions. Like,
yeah, okay, this is a really good question as well. So naively, if you think of like this bucket brigade circuit that I showed, it has like 2 to the n gates. So if each gate had like epsilon infidelity, you would expect it to have infidelity epsilon times 2 to the n. And this would be really bad, because then each component has to be like exponentially good. But a previous result from that paper where the figure came from is that there's a noise resilience where the particular structure of this particular circuit has a property that the infidelity only goes as epsilon times n squared, which is like it's a really important part of the narrative.
With post-selection?
Nope.
What's the intuition? That seems...
The intuition is that for a particular address, you only activate one branch of this binary tree. Like each of your data entries is stored at a leaf of the binary tree, and you activate one path, and the path, but you're actually activating a superposition of paths. You activate one path for any particular address, and if an error happens on another path, it doesn't actually degrade the fidelity of that query. And now you might ask, like, okay, but there's gonna be superposition, so you're really querying all of them at once. But the way it works out, you can still recover this nice error scaling, where like if every component fails with probability epsilon, then the overall infidelity only scales as epsilon times n squared. Yeah. So it still scales with n. So like there's still like an unscalability aspect of it, but we're never gonna need n to be more than like 50, right? So it's not like that asymptotic. Yeah, maybe last question, and then we can move over to other questions. But yeah.
So if I understand correctly, the main reduction says that instead of having to do a full-on QRAM query where you can have an arbitrary input state and have to put the plus minus ones, it's enough to be able to just go from 0 to a uniform superposition of the database. And then this whole thing says that then I can do all the QRAM queries that I want somehow. Right?
Yeah, that's correct. And the only thing I would add is that you do need this like adaptive update
measurement. But this, you only do n. of them.
Yeah, that's right.
Because you said that your degree is up to n, which means that the moment I have superlinear number of queries or something, right? Then I don't have to multiply this with poly n, right? Or am I wrong?
I didn't quite understand the last comment.
So you say I pay 2 to the n classical computation every time I have to change my basis. But this happens up to n times.
For each query, yeah.
I see.
Yeah, for each query. Because the next query, you might have a different set of measurement outcomes. So you might have to do different. Yeah, you have to do this every query. Okay. Yeah, you can view this as like trading quantum for classical complexity, which is sort of a good trade often. Yeah, I don't know. In the paper, we look at some other things like whether this update rule can be parallelized in applications, but I won't get into that here. I'll pass it to Andras. And I just wanted to mention before I pass that the algorithms team at AWS is hiring for a full-time position. So if you're interested, you can look online or you can email me or talk to me. Yeah. Okay, and now I'll switch over to this. Is that right? Oh, it showed up here.
We have to edit first.
It's coming. Why is it not going? Why did it? Let's see. Wow. Yeah. Works. Yeah. Still works.
All right, can you hear me? Okay, so now I'm going to talk about once you have your the, encoded state, how you get rid of the noise. And this is the distillation. So Alex mentioned that there is some twirling happening. And this is to make sure that despite there being some noise, the signal, which is the correct resource state, is still there with some small fidelity. And the twirling kind of makes sure that the resulting density operator that we get after all this noise coming from the noisy QRAM device and so on, it will preserve that I get a density matrix, which is now encoded in an error correcting code, and the density operator has the correct top eigenvalue. So the largest eigenvector in my density operator is going to be the desired QRAM state, and all this twirling ensures that that the noise is, although it's not exactly depolarizing, but qualitatively not too far from it, so the error is roughly spread out evenly in all the other dimensions. But still, the signal being here the desired QRAM state after the query is still there, and that is the most prominent of the in the mixture of this quantum state that I get. And so we can move to an abstract problem here, which is what I will show how to solve. So now at this point, we just assume that all the distillation operations are noiseless because we can just do that within the error corrected code. So we don't want to worry about noise anymore. Everything is error corrected from now on. So what's the problem? We get copies, any number of copies which of some unknown qubit state, and we want to prepare the top eigenstate, which is psi1. I ordered these p1 eigenvalues in decreasing order, and I want to prepare this with precision epsilon. Epsilon is the parameter that I can set. So what's the complexity of doing that? And this question has been studied before, and it was termed quantum purity amplification. And let's just consider a scenario which is fitting our setting that we know some lower bound on the top eigenvector, so that it's not too small. The signal has at least strength gamma, but we also know that the second largest eigenvector is not too large. It's at most half gamma, so there is a convenient gap between the largest eigenvalue and the second largest one. This is a reasonable assumption, and it is satisfied in our protocol due to twirling. And so the known optimal sample complexity when the precision, the desired precision is tends to 0, it's known by this paper of the same title, Optimal Quantum Amplification by Li, Fu, Isogawa, and Shuang from last year. And well, the optimal sample complexity is 1 over epsilon times this 1 minus gamma over gamma squared plus a constant. But this is an asymptotical result. It holds in the epsilon tends to 0 regime, meaning that this in particular doesn't say anything about what happens when the error is constant, say, or something like that. And the algorithm that achieves this and the arguments are relying on the Schur transform, and that means that they are processing all copies in parallel. And that's very undesirable, because then it would mean that you would need to like keep a lot of these resource states in your memory in the protocol, and that would be not so nice. So we were also looking at a different approach, is the iterated swap test, where they take 2 copies of this input state and do a swap test, accept only the 0 outcome, and then you get something which actually magnifies the top eigenvalue. So this is a very nice and very simple protocol. And imagine that you iterate this. So it has like in a binary tree structure, just pair up your initial states and then run a swap test and select, and assuming that you got the right 0 measurement outcome in ancilla, then that is going to be like the first iteration of your density operator, and you iterate until you get to a high enough fidelity. And so you can analyze this procedure, which was proposed by Childs, Fu, Lang, Li, Ozos, and Vias in 2023. And they showed that for depolarizing noise, when the top eigenvector is close to 1, it actually works very nice. But unfortunately, the performance decays exponentially as the fidelity goes down of the input state. And so we looked more closer to this protocol, and we just looked at it and showed that you don't have to have this depolarizing assumption. A set of authors showed the same thing in parallel, and then you get this complexity, at least in the case when you have the fidelity is already close to 1 and just you want to make it even closer. And it actually achieves the optimal sample complexity that I showed before. So this is an algorithm which doesn't require processing all copies in parallel, but still achieves the asymptotical complexity in a much nicer fashion, but only applicable to large values of input fidelity. And so we wanted to actually, and the brief comment here is that it's gate efficient because you just do the swap test. So basically the number of gates is the number of copies that you consume. And also, it seems like in this binary tree, you would need to store all the copies when you do it. But in fact, it's sufficient to store a copy of a state from each level of this binary tree. So actually, the memory requirement is only the logarithmic. It's also nice. But we wanted something even nicer. And so we devised a new protocol, which is based on the quantum principal component analysis ideas of Lloyd, Moshani, and Ravenscroft. And our protocol actually uses only 2 qubits plus 3 qubits. So we only ever need to store 2 copies or 2 partially processed copies of this input density operator rho. And it's also gate and sample efficient. And the complexity is just here. It actually matches the known asymptotical sample complexity bound in the small epsilon regime, and it's also reasonable in the constant precision regime. So the whole idea is based on density matrix exponentiation and Kitaev's phase estimation. So imagine for a second, now we have the rho. Rho is our unknown density operator, and we wish to find its top eigenstate. Imagine that we could, for some reason, do Hamiltonian evolution, where the Hamiltonian operator would just be the density operator itself. And density operator is positive semi-definite, in particular Hermitian, so you could just call it a Hamiltonian matrix, why not? And then suppose that someone magically allows you to do this Hamiltonian time evolution with the Hamiltonian density operator, you could just do phase estimation on it. And because we have some promise on the top eigenvalue, at least gamma, just run phase estimation, see if you see an eigenvector, if your phase estimate is saying that it's about gamma eigenstate or at least gamma, then you know that you found the right eigenvector and you are done basically. Now, there is some chance that you will find an energy estimate which is smaller than gamma half, then you know that, well, I am unfortunate, it's the wrong eigenstate, then you just repeat and get it more and more. Okay, but this assumes that you can do Hamilton evolution with this density operator, but you can only get copies of this density operator. So how do you convert between these two models? And well, that's really the key idea behind these quantum PC results.
Quick question.
Yes.
Was a qubit for the density matrix?
Yes.
Okay, thanks.
The qubit is the density matrix basically. And we store basically one copy of the density matrix and one partially processed, which was like already filtered by this like phase estimation like procedure. So yeah. So here is the density matrix exponentiation procedure. So on the left, you see is the simple version. Actually, to time evolve with rho to a small time t, what they proposed is just do a partial swap, this like small amount of swap, e to the I swap t, which is the swap gate exponentiated. And then it turns out that this will approximately implement a time t evolution with rho on sigma. So sigma is the qubit on which, or like qubit on which you wish to apply Hamiltonian evolution, and rho is the copies of rho that describes your Hamiltonian in this case. And okay, how do you like this partial swap? Actually, it's a very simple gate. So the gate on the right-hand side is actually what we run. And that's almost like the swap test, just 3 times, because we have, as opposed to 1 controlled swap, like in swap test, we have 3 slightly more complicated, but essentially the same circuit that we run. So yeah, basically we just do a weak swap and repeat it many times to get to the time needed for phase estimation. And so turns out that if you choose the right parameters in the circuit, then this is just going to really approximate time t evolution up to an error which is t square. So if you want a more precise approximation of this time evolution and phase estimation procedure, you just need to take smaller steps. It's very similar to the scaling of errors in Trotter and all these product formula applications. And an additional property that we use in the analysis is that actually, if your input state commutes with rho, then the output state is also commuting with rho. And this, in some sense, lets us ignore coherent errors. So basically, although there is some substantial imprecision in this protocol in Hamiltonian simulation, it will not really mix different eigenstates of the Hamilton of the density operator, and this basically means that we can just analyze our density operator in a probabilistic fashion, that either I got to begin with the largest eigenvector and I realize it, or I got something else and I also realize it in this phase estimation protocol. And this all works despite these inaccuracies and errors that are introduced here. And so basically, which I didn't have time to tell and go into details, the circuit that you see here, we just iterate on these circuits with various choices of t until we basically we do repeated a number of phase estimations with like increased precision. And first we just filter out roughly the small eigenstates and getting more and more precise as we go. And this ensures the state gate complexity. So at a high level, it looks very similar to the iterative swap test. But the key benefit is that I just always run this circuit with some parameters that are appropriately chosen in advance. And as you can see, the new copy of rho enters this picture and only lives there for like three controlled swap gates and then exits the picture. And I just like get new copies all the time. And sigma in, sigma out, that's the register where I keep refining my input density operator and getting towards the pure state, which is its top eigenvector. And therefore, I never need to store more than 2 qubits. These are on the circuit already, and they are just some few qubits. There is 2 qubits that I didn't show for like control operation, because this just shows you how to do Hamiltonian simulation, but for phase estimation, we need controlled Hamiltonian simulation, and that just adds 2 more qubits. So nothing particularly fancy. And this is only quantum circuit you do. So once again, to wrap up, you will get a third version, a third noisy version of your QRAM resource state that by getting more and more of these third noisy qubit states, we just refine until the fidelity is like 1 minus epsilon, good enough for our purposes, and then we just move to the logical level of the circuit and then run the protocol n times that Alex mentioned. And so the error scaling is not as great as we would wish. This is 1 over epsilon. In error correction cause, usually you get logarithmic overheads in the precision, and here you get like 1 over epsilon, which is degrading the performance somewhat, but it's still hopefully tolerable. So it basically will mean that you get an overhead which is like proportional to the length of your overall circuit. So how many times you need to apply a QRAM gate, maybe you need to apply the square of many times the raw. So like, suppose that you have a T-query algorithm, which uses QRAM T times, then up to the other factors that Alex mentioned, it is going to be like T square application of your noisy QRAM. And the key thing is here that you can control the error, unlike previous results that if you had some amount of fidelity in your noisy QRAM gate, then it gave a hard bound on how many times you could apply that gate, and with more QRAM applications, you would be just totally screwed. And that is it. Thank you.
Any questions for Andras?
So it seems like there's also an added benefit in that we've actually pressed a lot of the implicit T work into the physical level, right? Like another way of looking at this work is we're preparing exotic multi-qubit magic states that just happen to be the RAM exactly that we love to load, right?
Yeah, that's right.
So then does that mean that we could also think about extending that idea to other parts of computation beyond QRAM?
Possibly so. QRAM is very natural from this perspective because this is an operation that happens in so many applications. So that's why people build like classical RAM device is a very special purpose classical computer. But because it's like so ubiquitous that you want to just retrieve a memory element, that it's worth really developing a hardware just for that.
Yeah.
But if there would be some other operation, I don't know, QFT, whatever, maybe that's too simple in a quantum case, but something more complicated, you could imagine that maybe there is a way. But okay, one very important element here that Alex stressed, that we really rely on this noise resilience of the QRAM circuits. So somehow the noise does not accumulate to the number of gates, but only with the depth, which is logarithmic. And that is what makes this interesting, because the noise accumulates far less than you would naively think.
Okay, and so that means that we would think about for more general settings, either you would need to see that asymptotic behavior like you've described, or the constant factors for constant size instances, right, are good enough that you would do this.
Yes.
Okay. Any other questions? If that's not the case, please let's thank Alex and Andras again. We have one more coffee break, and then we have the last talk of the day by Greg, and then we have the reception.